freaking amazing.
I'll try not to freak out.
Hello and welcome to the Hackaday podcast. I'm Elliot Williams.
And I'm Al Williams.
This is episode 312, Heart Attacks, the Speed of Light, and Self-Balancing. This week in the news, one of the big scare stories that made the popular media was a critical flaw in the ESP32 Bluetooth stack. The firm was calling it a backdoor originally. It ends up being kind of a nothing burger. We wrote that up. You should go read our coverage of it. But basically, the short story is there's kind of two software layers, one closer to the hardware, one closer to user space. You could get in between those two and use some of the debug commands on the bit that was closer to the hardware space. But of course, this means you have to be writing code on the device in the first place. And basically, it was if you wrote malicious code that used this debug feature on your own chip and flashed it to it, you could use the debug feature on your own chip.
Yeah, a lot of those turn out to be that way. I get a lot of stories and you say, well, if you take the chip out of the PC and, use a laser to drill a hole through the epoxy to get to the die, and you're like, well, okay, at that point, I'm less concerned, right? So there seems to be a lot of that goes around.
And this wasn't even really that. This was just some debug features. So on one hand, as a non-black hat hacker, it's kind of sad to see debug features closed up. They let you do things that you might want to do with an ESP32. So otherwise, in the news, there was a neat story. Jenny reported on it. Open safety in the auto business. Renault shares its battery fire suppression system. This is really cool. It's for electric cars, and basically they contain the battery in a case, and it has a little access port so that the fire department can plug their hose up to it and completely surround the battery in cold water, putting out the battery fire. And it's a great idea. They got it patented, and then they're like, well, everybody should be doing this anyway. But attached to this anybody should be doing it anyway, they said if anyone else makes improvements in it, they should also not subject these to patents. And so I thought that was a very weird, kind of almost Stallmanian move coming out of an auto manufacturer.
I love that you coined a new word for that, but good word.
You can't stop me from wording, man. And last but not least, I was just over at the site at Motion Lab Berlin, where we're going to be having Hackaday Europe. Those of you who are coming, I'll see you all tomorrow night. Tickets sold out early this week, so it's going to be a full house. Super excited about that. I was over there with all the supply frame people, design lab people, stuffing swag into bags. So there is lots of swag in bags to be had. They're still over there right now. Actually, I had to duck out to do the podcast. As always, shirt design's really nice. There's a bunch of, it's just going to be a lot of fun. Looking forward to the talks too. Can't beat it.
I wish I could join you, but my teleporter's on the fritz, so. And of course, the other big news today is it is 3/14, or is commonly known, at least in the United States, where it's not 14/3, it's Pi Day. And we'll have more to say about that later, but happy Pi Day, Elliot.
Happy Pi Day.
And what kind of pie will you be having to celebrate?
I'll be having 22/7. What will you be having?
So you're having approximate pie, I think they call that.
Good enough for government work.
This is a journey into sound.
What's that sound?
What's that sound?
And that brings us to What's That Sound? This week is a sound reveal week. So if you listened to the sound last week and had a guess, you are among 91 other respondents. So I'm going to have to sort through them real quick, figure out which ones are right and wrong, get back to you in a second. But meanwhile, Al can have a listen and see if you can guess what it is.
It's clearly a ratchet and then some kind of strike. I'm going to go with a Craftsman socket tightening up a Bolivian unicyclist's unicycle. That's my guess, Elliot.
Sorry, Colombian unicyclist, but you were so close. Where does that come from?
Oh, it's a British series called The Fall and Rise of Reginald Perrin, but yeah.
It is the mechanical shutter on a disposable film camera. So it's winding and then taking a picture with a disposable film camera.
Oh, well, I'm way off.
A lot of people said a camera. A lot of people said disposable camera. In fact, I think, frankly, enough people said disposable camera that I'm going to have to give it to them. Yeah, but I'm still counting up how many. This is going to take me a minute. I'll be right back.
You bet.
Would you believe a Dymo label maker? A lot of people said Dymo label maker.
Yeah, that makes
A
sense.
lot of people said Dymo label maker. It's probably a trademark.
In a shocking reveal, we find out that Dymo uses disposable camera guts in their label makers. So.
Exactly. Not bad. 21 people got it right. And that's if you reduce right to people who just said disposable film camera. There's a bunch of people who said, camera, but not disposable camera. And this one, so many people said disposable. I have to give you points for the extra precision there. I'm traveling, so I'm on my laptop. Do I have a webcam on this thing? If I do, I'll do that one.
I don't know. That's not your big ancient ThinkPad or ThinkBook or whatever, is it? That certainly doesn't have a camera on it.
It is my big ancient ThinkPad, my X220, and indeed it does have a webcam.
Oh my God. I thought it had like a card reader and a paper tape punch.
What does it have? It has DisplayPort. The thing that I always get flack for is it's actually got a VGA port, but I think that's awesome. It takes a picture of me with the webcam, hashes it, and it gives me a number back, and the magic number is 5. Good job, ancient webcam. Oh, congratulations to Little Johnny Tables. Advancing film and taking a picture on a film camera sounds like one of the plastic disposable types. Absolutely correct. Congratulations to Little Johnny Tables. Try again with our SQL database next time.
I was thinking the same.
I'll be reaching out to you, get your t-shirt size and mailing address, get you a t-shirt shortly. If you didn't get it right or didn't get picked this week, make sure to listen in next week when we'll have a brand new sound for you to guess at. Well, off to the hacks. I wanted to start off with Mir-sem-k's. Man, that guy's posted so many. What is his name? I really got to figure out how to pronounce his name. He's posted so many things on Hackaday.io, and here I am with Mir-sem-k. I hope that's close to right. Taming the Wobble, an Arduino self-balancing bot. And this is actually a really simple project, but I just love the self-balancing robot genre. What I like about it is that it's, just the bare minimum parts, right? It's a frame made out of core board. It's those cheap toy gear motors. It's an Arduino. Of course, it's got the MPU at the top and the battery at the bottom. He does everything you do with one of these things. He's, tunes the PID to make it stand upright, and by the end it does. So on one hand it's a really simple project, but it's still really impressive looking to people who don't know how these things work on the inside. If you think this is something you would like to do, this is reminding you that this is a super good weekend project. It's something you can cobble together with stuff you've got kicking around. Probably doesn't have to be that precise. Just get it done, and the code isn't that daunting either. But what it did, of course, was it sent me down the rabbit hole of looking at how many times we've covered self-balancing robots. And I actually went off looking to see if I could find the first time we had one of these projects. If you look it up, there must be 50 self-balancers on Hackaday over the years. And so I kind of wanted to figure out what was the first one. The oldest I found was from 2011. Self-balancing robot keeps things on the straight and narrow. This was a project posted on letsmakerobots.com, which I couldn't get to load, but I was on a train at the time. It's probably in the Wayback Machine. Probably absolutely worth your time to check that one out. But along the way, just found a million interesting takes on this. One that's called PityBot has actual potentiometers on it that you can use to tune the PID parameters. And so you can actually, in real time, tweak this robot and see how it wiggles more or less. I think that's particularly brilliant. There's a bunch of simpler projects. There's even one that did self-balancing without an IMU. And I was like, what? But that one's really clever. It's actually just got 2 IR distance sensors on the front and the back. And so it knows when it gets too close to the ground and it accelerates, and it knows when it gets less close to the ground and it decelerates, right? So the thing keeps itself in balance without using any smarts or any gyro. Hey, is that a self-balancer? You can quibble. But what was really amazing here is that from basically 2010 to kind of 2014, there was an absolute bounty of self-balancing unicycle designs. And people were making those left, right, and center back in the early 20 teens. I don't know what is up with that, but we covered like our fifth or sixth one. By the time in July 2013, we covered yet another self-balancing unicycle. So I'll throw that link in there too. Whatever happened to the self-balancing unicycle craze?
Maybe it's still a thing in Bolivia. I don't know. It's odd that I picked up a unicycle and you're talking about unicycles, but the thing about this one is I love the look of it. It looks like a shelf on wheels, right? So it looks like a little knick-knack shelf, and it just happens to be a robot. But I'm curious, you looked through a bunch of our old ones that we've covered. Does everybody except your IR guy use PIDs? Because I think, if I'm not mistaken, like the Segways and a lot of the other uber modern ones don't use PID, right? They use MPC, Model Predictive Control. But I can't ever remember seeing a hobbyist self-balancer that does that. But I may be wrong. I'd have to look at your links.
Ooh, what's Model Predictive Control?
There's a couple of different strategies. PID is just one of them, right? And in fact, you're the 3D printing guy. A lot of the newer 3D printing firmwares use MPC for temperature control. Well, we got 3 articles that come up on a search for it. I can't tell if one of them's from 2009 and does not look like a suitable. Well, we'll put a link into something for that. So essentially you have a model of the behavior and you do predictive control on it, which prevents you from having to have, like, for instance, in PIDs, there's a common problem called reset, right? So you have anti-reset wind-up strategies, because what happens is if you say, for instance, a sensor comes off, then you just wind up having the integral term just keeps getting bigger and bigger without bound, right? So all the real PID algorithms that you use for real things have some method to go, oh, wait, that's out. That's unreasonable. There's something going on. Don't wind up. I don't know if I understand MPC well enough to explain it in a 2-minute blurb on the podcast, but I'll put a link in the show notes for some more information on that. But as far as I can recall, I haven't seen a hobby balancer use that, and I think Segway uses that. I may be wrong. Perhaps somebody knows. There's also LQR, which is linear quadratic regulators. They're not very locally optimized compared to an MPC or a PID, so it makes me wonder. I don't know if a balancer with LQR would fail to balance, right? Because you got to have pretty good response time over the entire regime where you face plant, right? So
I'm looking at the Wikipedia page, and it basically says, yeah, you model the thing, and then you take the model of its future behavior into your current control decisions. You're always working on the current step, but you've got a long-run view of what your current actions will do to it in the future that you've got modeled in there. That's really neat. Probably really matters if, like, small changes make really big changes in the future. So if you've got some kind of weird super nonlinear system or something. I wonder if the reason we don't see that in self-balancers is it's just not necessary, because as long as they stay mostly balanced, PID certainly suffices. Or maybe it's just too much work, but it seems to me you could model the physics of one of these little self-balancing robots pretty easily. Maybe that'd be a neat project. If anyone out there wants to do a model predictive control self-balancer, send it our way. We'll want to publish it.
here's a small self-balancing robot, and the GitHub name for it is Segway. Surely that's trademarked. And I don't think this is actually Segway. But he talks about using LQR, ILQR, which I don't know, and MPC. And he's apparently got all of them. So I'll put a link to this, even though we don't have a Hackaday article on this. We probably should. Okay, my first pick this week was from Mark Linwitschik. I hope I'm doing that right. Mark Linwitschik, who actually decided to take a look at some satellite imagery. And I'm always fascinated with this because, you know, when I was younger, satellite data that was not nearly as good as what you can just go find on Google now was highly classified, and you'd be thrown in jail for showing it to people. And now you can go Google satellite imagery. But apparently a company, Satellogic, has a bunch of CubeSats with cameras, and they have an open data set, and it's gigantic. It's in a Amazon S3 bucket, and I forget, like I want to say 7 terabytes or 7, I don't know. It was a lot. It was plenty. And I guess it's not the entire Earth. It's different places that I guess people have paid them to go look. But he talks about the satellite system, which is interesting in of itself. they're supposed to have 300 satellites in orbit at some point, but I think they maybe don't have that many yet. But the amount of data you have to go sift through to get anything useful out of it is enormous. So I'm not sure, I'm not sure if this is something you're going to do on your laptop, especially your laptop, Elliot. He said he's got a 6 gigahertz Intel Core i9 with 8 performance cores and 16 efficiency cores. And, he's got big iron. And I think it was still fairly stringent for him to get to it. But looking at his data, and I have not verified this or anything, but I guess they've got about 886,000, almost 887 records for the United States, 428,000 in Saudi Arabia, 423,000 in Australia. So it doesn't cover the whole world, but there's plenty, and then you wonder, there's 244 in Barbados. You got to wonder what's the discrepancy, why, what was the reason to take 244 in one place versus 886,000 in the other. But it's just really interesting. And there's all sorts of things you could, in fact, do with that kind of image data if you're planning long-range drones, or I don't know, you tell us, what would you do with it? But I'm just always fascinated that, this would have been very expensive and probably government level and classified not that long ago. And now it's, it's sitting on Amazon and you can just go pull this data if it's interesting to you.
Yeah, just pull this data looks really hard. This is some serious, A, database work, but B, just kind of wrangling all this data into a format where you can assemble the pictures together is a fair amount of work. I mean, it's all there for you, but yeah, you're going to have to work hard to make it make sense. For instance, it looks like you have to know the satellite's orbits to figure out where they were at a given moment in time to figure out where the pictures are from. You have to do reverse satellite tracking. Wow, but you got to say the results look super, super amazing. And it's pretty cool that, like you say, it's really cool that this is just open data that's sitting out there.
And I think I read the open data is at 1 meter resolution, although I think they have finer possible resolution with their system, I think. But man, 1 meter resolution from orbit is, like I say, there was a time when that would have been the envy of everybody in that business. And now it's a CubeSat that you can just go grab stuff off of. So we're living in the future.
Well, my next piece is the strange afterlife of the Xbox Kinect. And this was an article written up actually in the newspaper, The Guardian, about kind of Xbox Kinect hacks over the years. I thought that was a really weird kind of mainstream reference to something that's been on my short to-do list for the ever and ever. And in fact, funnily enough, Maya Posh and I were just talking about this a few weeks ago. So I might have even fooled her into digging up a Kinect and having a go at it. So we'll see if a Kinect piece comes out of her in the near future. But what was it about the Kinect? Well, when it came out, it was really the only 3D camera that was that cheap and that easily available. And it did not take people long at all to figure out you could just kind of unplug it from the Xbox and use it yourself. That's really fun. I remember when it was brand new, we were looking at one of these things. It puts out a bunch of structured infrared dots, and it knows the distance and the geometry of these dots. The camera, of course, is offset a little bit from the dot projector, and so when a dot hits further back, it looks like it's in a different place to the camera. It uses kind of parallax of each of these different dots to figure out what the depth scene looks like. They were sold with video game consoles for some video game use that never really happened. And so, unfortunately, they got discontinued after I don't know how long. But they definitely made their way into the hands of hackers and amateur robot enthusiasts. I remember a dude at my hackerspace had a stack that he built up with a Roomba at the bottom and a Kinect at the top. And it was doing early simultaneous location and mapping stuff in our hackerspace. And he was teaching a class on that. I thought that was really awesome. Kind of the quick and dirty alternative to doing a full LiDAR scan. So instead of scanning each point, you just throw out a bunch of points and take an instantaneous picture of them. But because of that, it gives you kind of an instantaneous snapshot of what the depth map in wherever you are looks like. And so that's kind of cool about the Kinect. Man, I've got one up in my attic. I've been meaning to use it forever. And it's funny the other uses this comes to. The article points out, some non-hacker uses, which include things like apparently they're super popular among ghost hunters because when they produce wrong results, it looks like there's a ghost in your room. And maybe that's kind of one of the downfalls of the Kinect is that it wasn't always hyper accurate and the resolution isn't amazing because, it's only got so many dots to work with. That said, for the price, pretty awesome toy and something that I think every Hackaday reader should probably play with at one point in their life. And it's like my bucket hacker list.
Yeah, they just look so cool all the time that you see people using them for different things. And I always think, that's like you say, it's a project I want to get to, but it's not near the top of my list. So I don't think I have enough time left to get to the bottom of that list as it is. What's interesting, though, is that we see a lot of things like that come out for the mass market, don't really succeed in the mass market, but then kind of take over in our world. Look at the QCat scanner, right? How many of us still have a QCat barcode scanner that totally failed when Radio Shack was trying to give them away? Because, of course, that's what you want to do is scan the Radio Shack catalog with your scanner. But yet they wound up being used in a lot of different places, just not the way that Radio Shack expected. I don't know why we don't see more vision control stuff. You remember the Leap controller? That was an interesting one. And of course, every science fiction movie you see, they show somebody sitting in front of the computer, waving their arms, gesticulating wildly to move windows and, Minority Report, right? Throw the file over to the other screen and then do this and do that. We don't really see that. And I don't know, maybe it's like the voice control we talked about a couple of weeks ago. Is maybe it's really not practical in real life. It just looks cool. So it's a movie thing and it's never going to come to real life. But you would think something like Kinect could do that, right? It's watching you. So if you point at the screen and flick your finger, why couldn't it figure that out? And we don't see that very often, if ever. So my first hack of the week isn't much of a hack, but it's kind of a physics mathematics thing from Floathead Physics. And, before I dive into the details of it, I got to tell you, even if you just like to go see somebody who's very excited about what they're talking about, you really want to watch this video because he's extremely excited about this mathematical physics concept. His assertion is the reason you can't go faster than the speed of light is because you're already going at the speed of light. Everything's going at the speed of light. And he makes a pretty compelling case for it. It's based off a book, and he shows the book. So if you really want to dive into it, probably have to go buy the book. But you can't go any faster than the speed of light. Of course, science fiction people hate that, because it makes for boring stories. But it turns out what he shows is by induction. You say, well, if there's a 2D space and you were watching this, he shows an airplane, but you're watching this thing that's in 3D space and it's moving only in the third dimension. So it's just going up. The shadow under it, if you're a 2D person living in a 2D world, you'd say, well, that thing's not moving. There's just this spot and it stays in the same place in the ground all the time. But then if it starts moving a little bit off of the vertical, you're suddenly going to see it moving and it's going to be slower than the speed of light because it's moving at the speed of light going up, but it'll still start moving. You say, oh, look, now it's getting fast, right? If it goes completely parallel to the 2D surface, now it's going at the speed of light in that direction because his assertion is that everything's going at the speed of light. So if you go at the speed of light, now the shadow that doesn't move is on the height axis, right? So you can infer that, well, if that height was not height, but was actually time, and then the 2D surface is our 3D world, that everything's really just this shadow in 3 dimensions, and we're all falling through time, if you will, at the speed of light. It's kind of mind-blowing, right? So at the moment that you're moving through time at the speed of light, you're not going anywhere. But as you start moving, it's the same effect. Your shadow moves in 3 dimensions at less than the speed of light. And the more you're moving not, closer to the speed of light, then the less you're moving on the time plane. Now, is that right? I don't know. I'm not a great, I hate to admit it. I had an engineering education, so I had a lot of physics, but I don't pretend to really grok it. I just pretend to use it. But it makes sense. And like I say, man, he's certainly excited about it. It has some really interesting graphics. And whether it's right or not, it's certainly a mind-opening experience to go through that with him. So Floathead Physics, be sure to check that one out.
It's definitely mind-opening, and it's not that we're going at the speed of light in regular 3D space, it's that we're going at the speed of light constantly and never changing our speed in this fourth dimensional, where one of the dimensions is time space. And that is the trick. What's amazing, and I think the part that he quite rightly gets super excited about, is that this kind of one simple idea explains a lot of the weird stuff about relativity. Like, it explains why you see length contraction when things get faster and faster. They get closer to the speed of light, they, appear to shorten. It's because, the light reaching you from the front of it is a little further away than the light reaching you from the back of it. It's kind of like the Doppler effect in vision. It's also easily explained by, just the geometry of the situation where the thing is tilting over. More of its speed, more of its velocity is like tilted over into the three spatial dimensions and out of the time dimension. And that also gives you funny things like the twin paradox, because you experience time differently because you're going slower through time when you're going faster through space, necessarily. And what's weird about this and what's really cool about this is that it's all exactly right. It's all these kind of sine cosine things that you would get as if this were the case. To some degree, whether you're really moving at the speed of light through a fourth dimensional space-time, who cares? The math works out exactly as we see it, though. And so once you're stuck with that, you have to say, well, maybe I am. And I think that's where you end up at the end of this. But I really, really like the way it kind of, this one simple idea ties together a lot of the kind of weird stuff that comes out of special relativity. I did this sort of stuff as an undergrad, and for me, this was actually mind-opening. This is definitely worth a look.
Well, yeah, and that was the thing. Like, I knew the equation for time dilation, and I guess I've noticed, well, gee, it does look kind of like a right triangle equation, but nobody ever bothered to explain to me why that was, and this explains that, right? It actually makes sense that what you're really doing is calculating the right triangle, a squared plus b squared equals c squared. And what's interesting is I think he shows it as something moving up because he wanted to get the idea of shining a shadow through to the 2D world. So that makes sense. But the fact that you're going at a constant speed made me think more of falling, right? So it's almost like there's a big time hole, if you will, and time gravity is pulling us through that time hole at we're at terminal velocity, which happens to be the speed of light. And if that's true, I'm a science fiction reader and usually frustrated science fiction writer. I've sold a little bit, but not. I get way more rejections than sales. As the science fiction guy, I think, well, that's cool because that kind of makes you think, well, maybe there's a way to go faster down that tube, right? Just like you can fall faster if you put a rocket on yourself or something, right? There's a lot of ways to do that. So maybe in the future, that insight would let somebody figure out how to go faster. Still don't know how to do it, but maybe there's a story in that. I don't know. So
nah, his model absolutely rules that out, because the gimmick is that we're all traveling at exactly that speed all the time, and it's just in which directions you channel that speed, right? It's just how you turn that vector around. And so I think that's it. I think you can't go any faster or any slower than the speed of light in this fourth dimensional space-time in his model. And I think that's the part that's even weirder, is that what I think of as acceleration, which is, going faster in the 3D space, is really spending energy and or effort, force, to bend my vector down out of the time direction and into the 3D space direction. Some night when I'm not able to sleep, I'm going to be thinking about force, mass, acceleration, and the bending of my four-dimensional space-time vector.
I disagree that it rules it out, because you think about it, if you were, we're primitive in this space, right? So if you're a primitive guy and you're dropping rocks and you go, well, the rocks always fall at the same speed and nothing slows them down and nothing makes them go any faster. Well, yeah, that's because you don't know about certain things, right? And there are, in fact, ways you could put a parachute on the rock to make it go slower. You could put a jet engine on the rock and make it go faster. So I think we just don't know what parachutes and jet engines look like for that. That's my wishful thinking. I don't have a real I don't have an actual insight there other than to say it's a lot nicer to me to say, well, everything's moving at that speed now than it is to say there's an absolute speed limit. God does not want you to go faster than the speed of light, so therefore you will not. So I still have some hope that one day we'll break the light barrier, just like we broke the sound barrier. So
we don't observe anything that's going either faster or slower than the speed. Like everything around us obeys special relativity. And if you buy this analogy, that means that absolutely everything is traveling at exactly the same speed through space-time.
all dropped rocks fall at the same speed too, but that doesn't mean
I'm surrounded by rocks that right now that are not going at the speed you want them to be going. But we have never, ever seen anything that doesn't obey special relativity.
well, I don't think either one of us will live long enough to see if I'm right or not, but yeah.
Yep. Mind blowing.
And you got to admit, he's super excited about it too. So that was fun to watch. Even if you didn't care about the physics, that was fun.
Well, bringing us back down to horrible reality, Electronic Wizard's video, lies, damn lies, and IGBT datasheets. Now, this is something I'm sure we've all done. You look through like some kind of FET, or in this case, IGBT datasheet, and it says it can pass an infinite amount of current, in this case, 200 amps. And you say, wow, that's a lot. I'm going to totally buy this. And then you put it in your project and it burns up. And you're like, oh man, that wasn't nearly 200 amps. Why did this thing smoke? And the answer is, of course, also in the data sheet. If you read where it says, what its internal resistance is and how much heat it can dissipate, you can back out how much actual current you can put through it on steady state. This is like a pulse current rating before the thing fuses. And it's there for a reason. It's there because you want to know what the infinitely small spike resistance is of these devices. And I think the 200 amp spec is at, I don't even know how many microsecond pulse, right? So yeah, it'll do 200 amps if you like zap it for the shortest period of time. That's useful if you need something that's spark resistant, basically, but it's not, you're going to go powering a truck with this one tiny little transistor. So the video kind of takes the opinion that this is misleading in some sense. And I don't think it really is. I think it's that a lot of hobbyists misunderstand the intention of these numbers in the datasheet. I have absolutely no doubt that if like whoever this is, National Semiconductor or, International Rectifier or Toshiba tells me that their part is good for 200 amps at a microsecond, it probably is. But then, you're the one who's responsible for extrapolating this to its behavior over, reasonable motor driving time frames and stuff. I don't like the part of this guy's take that is, they're fooling you and that sort of thing, because they're absolutely not. On the other hand, he's not the first person to have been misled by this part of the data sheet. I've looked at these myself and been like, oh, I can pass 10 amps through this little jammy. But again, that's 100 milliseconds or something, So there's always a time rating and a kind of maximum energy dissipation rating and stuff like that. Those are the ones you want to look at if you're thinking of driving a motor with the thing. But I do agree with his basic point here, which is that when you read these data sheets, it's important that you know what the figures of merit that you are interested in are and not the other ones. In this case, that microsecond pulse just isn't what I'm after. So, look for how much heat it can dissipate over the long run, etc. Definitely read the data sheets carefully, but also don't fall into the trap that this person did and then feels burnt by, of assuming that maximum peak, like transient pulse current, is anything it can hold on a continuous basis.
I think that's fair. I mean, datasheet writing and datasheet reading is an art, And usually, I don't know if I want to go with always, but usually the people who write the data sheets are very, very familiar with what they are doing, and they go, oh, this is important because of this obscure thing. And, you don't necessarily have that same level of understanding for their parts. My story about this is very interesting. I think that, one of the things we see too with datasheet problems is you've really got to look at your whole system, and you've got to look at effects that we normally abstract away. So I always say that we pretend wires have no resistance, but in fact they do, right? And we pretend that batteries don't have any internal resistance, but in fact they do. I worked for a large electronics company many years ago, and a bunch of physicists, going back to physics, and they were trying to do some reliability testing on something, and they had a transistor circuit. And in that part of the company, we dealt with was stuff that failed, right? So it was failure analysis and, technology assessment for failure. So when all you see all day is stuff that fails, you just assume, well, this stuff fails all the time. So they came up to me, like I say, a bunch of physicists, and they said, hey, you're an electronics guy. What kind of transistor can we use here for the switch? Because we've had like 6 of them and they've all been bad. And I'm like, really? You got 6 of them and they were all bad? Yeah, they were all bad. I'm like, I find that hard to believe. Show me your circuit. So they show me the circuit. Pretty simple. They're driving a node to ground and basically drawing current through a bunch of test devices. And I hadn't realized just how many they were doing. So it turned out it was a very high current application. But, they told me what the current was. I looked at the transistor spec sheet and it was like, yeah, it's fine, no problem. But they were trying to do a certain amount of current there. So they had a little resistor, a resistor in the emitter leg of it to ground. So you assume you're going to have the base minus 0.7 divided by the resistor. That sets the emitter current. It's basically the collector current, and that's your current. So they were, they all have been bad. I'm like, I just can't believe it. I said, can I see it? So we go over to their lab. I look at it. Because it's such a high current thing, they've got like a 10 or 20 watt resistor in the emitter leg. Well, guess what? The resistor's wire wound, right? So, of course, it's an inductor. And so anytime you have any sort of little change in the base current, even like early effect current inside the transistor, you get a current change on the emitter, which causes a big voltage change based on nothing more than the time of that change, right? So suddenly you've got your reverse voltage, which, on the transistor, the reverse voltage is not very good. You've got 200 or 300 volts in reverse, and kind of like your IGBT, sure, maybe for a picosecond it could have taken that, but for a millisecond it blows up. So they were just basically instantly frying the parts. Actually didn't know it at the time, but they make non-inductive wire wound resistors. I do a little research, and this was before the internet. So, they either wind the windings forward and backwards, or they do 2 windings, one going one way, one going the other, so the inductance largely cancels out. So once we found those and put them in, mysteriously their transistors quit failing. So again, the data sheet had actually the data you needed, which was how much reverse voltage can you take. The question is you didn't think you had all that much because you weren't taking into account the other parts of the system, that the resistor wasn't perfect, it was inductive, that the transistor doesn't work as a perfect model like we modeled them, that it's got little variations in current. That was the thing. So I think that's a key point. You not only have to look at the data sheet and understand what each one of those pieces mean, but you've also got to look at the whole system and understand how they interact. And we frequently abstract that away, which is good mostly until it's not good, right? And that was a case where it wasn't good.
Like learning to read a data sheet, like burning out transistors because of weird inductance in your circuit. A lot of this is just stuff we kind of have to learn over time. And you either learn it in school where they warn you about this, or you learn it the hard way with smoky MOSFETs. One way or the other, you got to learn it. And the comments in this kind of go down these 2 different roads. Like half of them are like lambasting this poor video guy for not knowing how to read a data sheet or not knowing how to use the part. And then Janu comes in and says, no one is born knowing how to read a data sheet, you donut. People read this site to learn stuff like this. But I think that's right. I think no one is born knowing how to read a data sheet, and especially these little weird gotchas like this in a data sheet where it really looks like it's saying one thing, but if you don't double check the time axis on that graph, you're going to have a bad day.
I'm envisioning Obi-Wan Kenobi making a hand motion and saying, this is not the spec you're looking for. So I don't know. Okay, my next hack comes from Ernie Tech. And Ernie Tech is mostly, his YouTube channel is mostly about running mainframe software using Hercules. So, you can have basically an IBM 360 or 370 or 3090 or whatever running on your PC now, which is entertaining in of itself. But he had a different kind of thing, and it really appealed to me because I write a lot about these sort of things too. and it was talking about the earliest fictional computer he could find in a movie that was kind of like had sort of a human aspect to it, right? It wasn't just some blinking lights and a typewriter popped out. And I guess he had talked about Colossus a couple of months ago. Of course, we talked about Colossus last year. That's from the movie The Foreman Project. But he had found one, and I guess I had not really thought about it, even though I feel certain I've seen that movie sometime in the last 60 years, is Desk Set with Spencer Tracy and Katharine Hepburn. It's this big, unrealistic-looking blinking light computer, and Spencer Tracy's an MIT computer expert, and he comes to computerize the company, and of course everybody's going to lose their jobs, and there's a love story and all this other stuff. So this is in 1957. I think what was really interesting about it was that if you think about it, people back in those days, and even when I was a kid, thought that that's how computers worked. You know, that's what we always saw in Star Trek. You walked up and you said, "Hey, computer," which I probably just activated one of my devices. "Hey, computer, what's the capital of Algeria?" And it tells you, right, or whatever. We always said, well, that's ridiculous. That's not how computers work. But, now we've got the chatbots, and they do work that way. And you can basically go and ask a device something like that, and it'll probably answer you because it's got the internet behind it. There's a company called Sesame. If you go look them up, they have these chatbots that I promise you, if you talk to them for a few minutes, definitely passes the Turing test, right? I mean, it does not sound like even ChatGPT. It's a machine, right? But I think the other thing that really struck out about that is, there's a lot of angst right now about, AI is going to take all the jobs. People are going to be out of work. It's going to be a disaster. But, guess what? In 1957, that's why movies like this were popular, because everybody said, computers are going to take all the jobs. We're all going to be, destitute, living in poverty. We've seen that trope over and over again, even Star Trek, right? Gosh, I can't believe I can't remember, but the Multitronic 5 computer or whatever takes the Enterprise, and that they're all worried it's going to put everybody out of a job. But then, of course, don't worry, because it goes crazy and kills a bunch of people, so they have to take it back out. And it's kind of the same story here. Everybody thinks they're losing their jobs, but then the computer makes a mistake, and then everything's okay. So it makes you wonder if we're just not going through this cyclically, right? At first it's the steam-powered looms are going to take everybody's job, right? And then it's the the computers are going to take everybody's jobs, and the AI is going to take everybody's jobs. And it turns out none of those things yet have taken everybody's jobs. It's changed jobs, and I guess if the job you like to do isn't viable anymore, that doesn't make you feel better that jobs aren't all gone, just your job's gone. But, somehow humanity keeps plugging along and surviving. So anyway, just kind of a nostalgic trip for me. That computer set wound up in lots of other places, including the movie The Fly, which probably more people have seen than Desk Set. But it wasn't really a major character. I guess they just reused it because it was a lot of expensive blinking lights. But something to think about, though, is how people saw computers in 1957 and in the 60s with Star Trek, and then how we're kind of repeating that cycle again as we go through yet another growth spurt.
That's an absolutely beautiful looking movie prop. It definitely makes me want to have one of those. Like, I need one of these gigantic, it's like a blinking lights display, but even bigger than the one you thought, but also with a bunch of really awesome knobs on it. Just crazy multi-turn potentiometers and gauges and dials. If I were a movie prop maker, this is what I would make.
It reminded me of Sage. I don't know, when did Sage get built? Yeah, it was in the 50s. So I think somebody probably saw Sage, the IBM Sage, and it's very similar looking, in a not exactly, but it seems kind of familiar looking. It looks like the Sage console.
Okay, well, time for quick hacks. I'd like to start off with Sebastian Duel's Flying Cam is sweet DIY webcam on a stick. The gimmick here is that he made a nice 3D printed housing for one of those ESP32 cam modules, and it attaches it to an IKEA, one of those gooseneck lamp sticks, and has also a nice battery pack for it that goes around the base. The idea is you now have a webcam you can pick up, put anywhere, and just kind of point at whatever you want to watch. Flip the switch to turn it on. It fires up an access point and or hooks into your house's Wi-Fi network. and you are observing whatever it is, whether it's watching your pasta not boil over, or ad hoc watching a 3D printer run, or your kid gets an interest in the squirrel building the nest outside and you pointed at that. I think it's just an awesome idea to have an always available webcam on kind of a flexible mini tripod as a thing. The other thing he builds to go with it is a battery powered screen so you can see what it's showing at any given time. Of course, if you have a tablet, you can do the same thing with that, right? But I like the idea of the special purpose devices here. Next up, Simon Wilson, how to use LLMs for programming tasks. This is a really nice, I think, kind of balanced, very fair assessment of not just whether you should use LLMs to do your coding for you, but then how you would do it. It's not always going to get it right. You have to test what it's doing. But he also points out that it's this iterative development where it gives you the wrong thing and then you tell it to give it the righter thing and it gives you something righter and then you improve on that. Kind of nuts and bolts approach he takes here. Last up, Alex Lohman, some useful notes on the 6805 EC10 addressable RGB LED. I picked this up because this is the smallest addressable LED, I think, on the market right now, certainly that I've ever seen. And Alex is kicking the tires here. Just to get an idea of how small this is, if you're used to using the quote NeoPixels that are 50 by 50, there's a smaller version of those that are 3535s, which are 3.5 millimeters on a side, of course. These are under 1.5 millimeters on a side. They're absolutely tiny. And he does say that in his test assembly, while he was hot airing them down, he blew a couple away and they got forever lost. He suggests using low temperature solder and the slowest flow you can get away with on your hot air to keep them from blowing in the breeze. But he does end up making a high density and 10 centimeter long string of these things, and it looks like it's going to be really neat to drive that. So, if you want the resolution, if you need the resolution that ultra tiny LEDs can get you, you can get it.
My picks for this week, Joshua Coleman has his classy paper tape reader complements homebrew retro computer. So he's got the Coleman Z80 computer, and now he's got a really sharp-looking paper tape reader. I'm always fascinated where, when I was a kid, if you built something at home, it looked like you built it at home. And now with all the techniques we have available to us, you can make stuff that looks like this. And it would have made a good prop on the desk set movie. We could have used it for that. So Tech Minds, an interesting ham radio channel, is looking at a remote antenna tuner, and the article is what's wrong with this antenna tuner. He picks up a cheap Chinese automatic antenna tuner that's rated for 350 watts. And I don't know, maybe that's like the IGBT. Maybe it's only for 10 milliseconds. It didn't work as well as he hoped it would. And he was asking people if they knew why. So I had an opinion. A lot of the commenters had opinions too. But it was still an interesting look at a pretty well-built device. One of the things I noticed is that the inductors on that one are on toroids, and on a lot of the other ones, I don't know if it's just a newer version or if it's because of the power, a lot of the other ones, they're air core, and to keep them from talking to each other, they're at right angles to each other. So if you ever look on, eBay or whatever, and you see some of these, they'll have one coil's horizontal, one coil's vertical, the next one's horizontal. The toroids are self-shielding, so that presumably lets them just put them all together. But it's a pretty good looking device. It's tempted me to go buy one to play with, although I haven't done it yet. And last but not least, it was a very simple hack from Playful Technologies. The clock mechanism goes crazy for Arduino. And, it's not the first time you've seen this, where somebody takes a clock movement, takes control of it, and then, you can make the time go fast, or you can make the time go slow, or you can, do whatever you want with the hands on the clock. What I thought was interesting, though, is he had a really nice explanation of how those clock mechanisms work. So if you don't know how those work, it's well worth taking the couple of minutes it takes to watch that and learn something new.
All right, well, that brings us to our Can't Miss articles. These are long-form pieces written by our fantastic Hackaday writing staff. This week I wanted to start off with Maya Pasha's Pixel Watch 3's loss of pulse detection. the algorithm to tell if someone is dying. Was in the news recently because the loss of pulse detector feature in Google's Pixel Watch got FDA approval recently. I'm not 100% sure what that means. I'm not a medical lawyer, but it sounds like they have decided that there is some medical worthiness to this device and it's not just a gimmick. Basically, the phones have a motion sensor, a pulse sensor, and an oxygen level meter. And so you can imagine combining these three things together to see if a person is in distress or not. And I think that's part of what's really interesting here is that problem of determining if someone is having a cardiac failure is actually really hard from something like a wristwatch. If you do the stupidest thing, like, oh, there's no pulse, what if the person just took the watch off, right? Would that be their pulse went away? Are they dying or did they just take their watch off? Or you do what Apple did with the phones for a while, which is you put an accelerometer in there and then you get false alarms when people go on roller coasters, right? They're not in a car wreck. They just are, at Six Flags. But by combining all these together, you kind of start to get toward where you can make a more reliable, oh dear, this person is in serious medical health problems indicator. And then the question that Maya raises here is what can you do about that? How quickly can you get someone out there to save them? That, of course, matters a lot. And, should you be sending off emergency messages every time it crosses over whatever their data thresholds are? And that, of course, I don't know the answer to. And I think it actually probably is an open question. They're definitely doing the research to try to make this a useful device for detecting human crises. But like Maya points out in this article, if you see someone fall down and then go and take their pulse, you can see if their heart's beating or not, and then if you need to administer CPR. But the first thing you saw there was this person suddenly pass out and lose consciousness, right? Like that's the sign that warned you that something's wrong. And then you go figure out their pulse and take it from there, right? Then that's diagnostic. But like you don't just go around testing everybody's pulse who walks down the street. And I think that's part of the problem here. And down in the comments, creator with a 3 for the E points out the kind of statistical problem here. And that is that not very many people have life-threatening heart attacks, but a whole lot of people have Pixel watches. And so even if the false positive rate on the Pixel watch is really low, even if it's doesn't detect, if it's only 1% false alarms or something, that's going to absolutely flood the number of real cases that it detects because the real cases are just few and far between. And this is one of those unfortunate facts about false positives and false negatives. When the disease or the event you're looking for is very rare, you're going to get a lot of false reportings relative to how many correct, true identifications you get. And the question here is then, does that swamp the EMTs with false responses or not? And I think this is something, we're going to hash out as a society, whether this kills emergency medical services if these watches like auto dial them that the person has had an accident. It certainly is the case that like Apple started geofencing the phones when they were doing this to keep them out of amusement parks because they didn't want people to be reporting crashes all the time they went on roller coasters. So, there may be some other factors that need to be taken in here. But even if you do that, all they can do is reduce this false positive rate a little bit. But again, if the ratio of people who don't have heart attacks to people who do have heart attacks is pretty large, and I think it's really large, you're always going to get more false positives than you are true positives. And that cold hard Bayes' rule here may limit how possibly useful this kind of idea is. Bayes' law. That's a law.
I'm really surprised when I see anything like this. And of course, I got to warn you, I'm a terrible predictor of the future, right? I never get the future right. I walked in a Starbucks years ago and thought, well, this will never turn into anything. And, here we are. So I often think when you've got stuff like this that's life and death, it seems like it's just a giant lawsuit magnet, right? And I've said that about self-driving cars, is you could knock the accident rate down to one person a year dies in a car accident. People will not accept that, right? They'll accept thousands dying by human hands, but if the computer kills one person, it's a travesty. And it's the same thing here. I would be so fearful that when my watch fails to realize I've had a myocardial infarction and doesn't do anything, that my heirs will just, not necessarily my heirs, but somebody's going to go, oh, grandpa didn't get a notification that he was having a heart attack, so therefore we're suing everybody in sight. And I think they could win. So I don't know. Maybe there's some sort of safe harbor provision that's been worked out, or because it's got FDA approval, or I don't know. But it does seem like that's a real issue. I do think there are some of these services, though, Elliot, that don't, and I don't know about this one, but they don't directly call 911, right? So the new Pixel phones, for example, have some sort of satellite service where if you don't have any phone calls, phone service, it'll come up and say, if you have an emergency, do you want to use the satellite service? And it connects you to an operator through text messaging. And that operator, I think, makes the determination that, oh, yeah, you're having an emergency. I will call the local authorities for you. I don't think it just directly Joe Bob at the 911 office, wherever you happen to be out in the hills. So maybe it's something like that. But I don't know who's paying for that. Who's the third party that determines, oh, yeah, you're really having a heart attack? And what's the liability for when you don't? Because I agree with you. It's super difficult. It's one of those things like, is that thing alive? 4-year-old kid can look and say yep or no, but it's really, really hard to make a computer or a remote spacecraft go, oh, yeah, that thing's alive. It's a much more difficult question than it appears on the face of it.
Yeah, not to get too deep into the statistics weeds here, but it's one of my particular weed patches. This kind of test is really good for identifying a potential problem for an investigative study. But then you want to, like you said, back up and do a case-by-case investigation afterwards. And so, like you said, if the phone thinks that there may be a problem, you pass it over to a human who then can identify the situation, yes or no. And that's, of course, the right thing to do. For the longest time, it was the AIDS test was one of these, where it had a false positive rate that was something like 5%, but the rate of people with AIDS in the population was some 0.00 something percent. And so it was like 10 times more likely that you would get a positive AIDS test result back than you actually had AIDS. Right. And so you just go and you take another test, and then you take another test. And so you take 3 of them, and that kind of whittles the odds down. If you end up getting that many false positives in a row, then you're kind of in trouble. So this device, I think, in a very similar way, is really good for a screening. It's really good for a first level, hey, this might be a problem. But then you do have to pass it on to a human. You can't just automate the system after that.
If you are having a heart attack, select all the pictures that show a school bus. Sorry.
Yeah, right. I think in the end, it's a really neat problem, and I think the approach is kind of right. I think the approach of taking a bunch of different sensors that sense a bunch of different parts of how you're doing and trying to combine that together into a holistic picture makes a lot of sense. And I think that kind of idea is the best thing you can do. But because of just the odds here, I do think that it's kind of also only ever going to be a screening device and not a final decision of whether the person's having a heart attack, or at least it shouldn't be. On the other hand, if you're a person who is known to be at risk of having a heart attack, you might want an always on screening device. Like if you're in that health bracket where having a heart attack is likely, heck, you probably want something that's always screening and always making sure you're doing well, because the cost of a missed positive is even worse, right? Like if you have the event, you want to get treated as fast as you can. So the screening's totally useful, and I don't mean to belittle that, but it's just a really difficult problem, and I think it's neat to see them trying to solve it.
Well, in honor of Pi Day, I picked my own article. You know pi, but do you really know E? Everybody's memorized pi. Well, I say everybody. All the dirty guys have memorized pi at some point in their life. If you haven't bothered to memorize pi, I can help you out. As the sentence is, may I have a container of coffee? And if you count the number of letters, right, may I 3.1, and you just keep counting. But the problem is that really shows a lack of understanding, right? If you say, what's pi? If you ask somebody what's pi and they say it's 3.141, they don't really understand it. That's certainly the numerical value of pi. But the real answer is, well, it's the ratio of the circumference to the diameter of every circle in the universe. And that's the understanding part of it. What the actual number is less important, at least in my opinion, than that. I'm a real stickler for that. There's been many times when I've had people show me a number, we're up 33%. Well, what is the thing that's up 33%? And they can't explain it, right? Or you show a graph and it's like, what does that graph represent? Well, I don't know, but it looks good. It's going up. I got to thinking about other numbers that people don't understand, and I decided to talk about E, which is the base for natural logarithms. Sometimes it's called Euler's number, although there's also Euler's numbers and there's also Euler's constant, which are all different things. So I'm not sure why that's so confusing. And I think the number was originally discovered by Bernoulli, so why it's not Bernoulli's number, which there are other Bernoulli numbers too, so maybe that's why. But if somebody says, what's that number? What's E? And you rattle off 2.71, whatever the next number is. It's like pi. I mean, that's not incorrect. It is that number, but it's not what it means. And so what I tried to do in this article was kind of show what E actually is. And of course, the textbook definition is it's the base rate of growth for any continually growing process. But I don't know about you. If you didn't already know what that means, that probably doesn't help you much. And so the example I go through starts off with money, but in fact, it applies to almost everything. And by the end of the article, I'll make the case that, if you've ever heard the rule of thumb that, well, a capacitor and a resistor will be at 63% charge in one time period, right? The RC time period, or it'll discharge to 37% over that same period. It turns out E is the reason for that, right? The equations that I talk about here would allow you to calculate that and not just know it as a rule of thumb. The idea is that, the money example, going back to that, the idea is that if you had interest on so much money that it would be, say, take a year as an example, then you'd say, well, here's the money, here's the interest rate. After a year, I have this much money. But if you say, well, no, wait, let's compound that. Let's go every 6 months and say, okay, you would have, the example I use is $100 at 10%. You say, well, okay, $100, 10% of that's $10, but that's a year. So at 6 months, it's $5. So now you have $105. Then at the end of the year, I go, okay, now you've got $105. What's 10% of that? Well, that's $10.50. So you add that together. Now I've made $110.25 instead of $110. So compounding helps you because the money works harder every day, right? Or every compounding period. And that's the thing. If you compound monthly, you're going to make more. If you compound daily, you're going to make more than that. So the idea is, when does it just go up forever? And the answer is no, right? It'll eventually limit out because the dividing the interest payment by whatever that number is makes it so small that even though there's more of them, it doesn't make any more practical difference. And the amount of growth that is 2.718 or whatever it's a transcendental number, so it goes way out to infinity. But that's the maximum you could possibly get. So if you do the math, the most you could get at that 10% is $110.50. But if you compound it every month, it's $110.47. So it's the maximum, right? But that applies to so many different things, and it applies to things that double or go up a certain amount, stuff that decays like radioactive material or populations of bacteria dying. All those things relate to E. And like I said, capacitors too. And I can't tell you how long it was after having a very good engineering education where I could have told you what E was, but I didn't really understand that very simple idea that it's that limit to growth or decay on an exponential number. And I read a website years ago, I want to say it's called betterexplained.com. I'll throw a link to it in the show notes. And it kind of set that up. and I think there's been several YouTube videos I've seen since then of some of these math guys talking about it. But it's incredible to me that in all the math I had in school, no one ever explained that in that way. It kind of comes back to what we were talking about earlier with the abstractions, right? It's easy to say, well, there's a resistor and it doesn't have any inductance, except it does, right? And people tend not to tell you that. That's something, like you mentioned, you kind of learn out on the street. So even though it's Pi Day, I figured everybody knows Pi, but I really wanted to do a deep dive into E, and I'm sure many, many people knew that, but my experience has been many people don't know that too. Elliot, I know you've had a lot of math. How about it? I'm sure you knew that given your previous life experience, but have you found that everybody knows that, or you think just some people know that?
Oh, I don't know what other people know. Let's see. I've definitely taught college classes where people don't know what E is about, and like on a deep level. And E is actually really beautiful because, like you say, it's, you put money in a bank, you get interest on that money, you get more money in your bank account, so you get more interest the next period. Or you have some bacteria growing, right? You have 100 bacteria, 2 of them grow. Now you got 102 bacteria growing. More bacteria are going to get born the next period, right? And then because more get born, there's a bigger population having babies, and they make even more the next period of time. This is this kind of exponential growth or decay kind of thing. And it's anywhere where the force that's making the growth happens grows as a product of that growth, right? Like, so it's the number of bacteria increases, the growth rate increases, which increases the number of bacteria. Or to take your capacitor example, which is a great one, right? If you had constant voltage, you'd say, oh, well, this much current flows. But with a capacitor, you're draining the charge off of it, right? So this much current flows out of it. Now you've got a lower voltage, so less current's going to flow out of it. Now you've got a lower voltage still, so less current's going to flow out of it. Now the voltage is dropped even lower because of the current flowing out. And that kind of interdependence of the thing that's providing the force that's making the flow of electrons go out, and the flow of electrons itself depleting that force, is what's neat about E. And I think that's, dude, I'm with you. It's one of the most kind of beautiful mathematical numbers, I think, mostly because of this idea, because it captures this growth idea, growth or decay idea. And because of that, it's in all sorts of systems, where there's this kind of feedback between the action you're looking at measuring and the force that then causes this action that you're looking at measuring. And so you see it everywhere. It's a great number. And, when people mess around with exponential growth and say that, I think they say it metaphorically a lot more than they mean it. But the condition for exponential growth is that the thing that's doing the growing grows as a result of the growth, right? And so it kind of feeds back on itself. And that's what makes it take off so fast. And that's what makes e to the whatever go off to infinity so darn quick. Well, that brings us to the end of this week's Hackaday podcast. Thanks very much for listening. If you want to follow the links, head on over to hackaday.com/podcast. And if you see anything cool or do anything cool that we should be writing up, shoot us a line, tips@hackaday.com. And until next week,
keep those hacks coming. Supposed to wrap your head in gaffer tape. Let me clear my throat. You definitely want to watch this video. He's extremely excited about it. Oh shoot, did that come through my microphone?
Loud and clear. Lies, damned lies, and LGBT. Oops, I said it. Well, the fall of American civilization brings us to quick hacks.